Hale telescope at the Palomar Observatory in California. 5 meters across by 17 long, the Hale is among the world's largest astronomical telescopes. The human urge to reach the very edge of space created this enormous instrument. Telescopes discover worlds so far beyond our own that galaxies of stars light years across look tiny. As we push our knowledge to the boundary of the universe, we are also turning telescopes around, in a sense, to look at inner worlds of tiny things. This might look like a telescope. In fact, it is the largest electron microscope in the world at the University of Osaka in Japan. Where telescopes look outwards in their quest for other worlds, microscopes seek hidden worlds within. Worlds within worlds within worlds. First microscopes, then electron microscopes, now scanning tunneling microscopes have improved our insight into nature's microscopic worlds. We have reached the point where we can see single atoms, the basic building blocks of the material universe. This is our eye through the darkness. With each advance, we probe more deeply into nature's secrets and her soul.
The strangest thing happened to me at the studio today. We just finished taping the morning session. I sat down for lunch, and this voice started talking to me. It seemed to be coming right out of the box.
Welcome to Nanospace. Let me be your guide through these worlds within worlds. Nanospace is everywhere. Everything is built upon it. A human being or a pickled plum, all nanospace. To scan the surface of a plum is to explore an alien space as strange as any jungle. Take this rock in the undergrowth, a crystal of common salt. And here, take a close look at the wood in a chopstick. The living tree drew water to its leaves through these small tubes. Rice with sesame seeds. Up close, familiar seeds look different. Their surface is as broken as a space-lost asteroid. How to describe nanospace? It's a series of ultra-microscopic worlds, where common things take different forms. I'm sorry, I didn't introduce myself. Your guide through the uncharted waters of nanospace. Like Argonauts of old, we're going to travel into unknown worlds. This elevator is the strange, space-shrinking craft that will take us there. We'll call it Nanogate, for that's what it is. A gate into the ultra-tiny worlds we see beyond the microscope. The floor I'm standing on represents what we consider normal size, the world where we live. Each lower level shrinks us by 1/10. Of course, each floor is a world in itself, scaled to its own special scheme of things. Those near the top are rich in life. Further down lie worlds of molecules. Below that, we find realms where single atoms travel at the speed of light. Nanospace will offer you experiences you never dreamed of. Let's stop here on our fall into nanospace. I should explain. A nanometer is 1/1000th of a meter, and that's where we are, in a world 1 billion times smaller than our own. This is the realm of the elusive atom, making it the most challenging part of our tour. Perhaps on a first visit we should look at something more familiar. We're back in a world where I'm 1.7 millimeters tall, a little thicker than a thumbnail. Good grief, this world is full of surprises. And hazardous. I'm not much bigger than a water flea, a prey for every passing fish. Especially this minnow-sized monster. At this level, we're still in a visible world. But now let's go down, shrinking to a size where the world is measured in tenths of a millimeter. At this point, we become no taller than the thickness of a razor blade. One nanostep above, we were about the same size as this flea. Now it dwarfs us. This is an elephant water flea. Not called that for its size, I hasten to add. It's named for the shape of its proboscis. Our visit is well timed. The mother flea is going to give birth to a clutch of babies about my size. Scaled-down worlds in nanospace are no less rich and complex than our own. These rotating spheres are planktonic plants called volvox. Each sphere, the size of the ball in a ballpoint pen, is a colony of as many as 500 cells. Each green patch is a single cell, given its color by chlorophyll. Every cell on its surface beats little hair-like flagellae, giving the colony its spin. Like galley slaves pulling to the beat of a drum, the work of Volvox's 500 cells is coordinated by some unknown force. The one in red is me. The others are rotifers, animals which sweep the water with a ring of bristle-like cilia around their gullet. Their cilia work like turbine blades, driving water rich in food particles into the body cavity. This streamlined predator, Paramecium, devours bacteria. A hunter-killer of the microscopic world, it's a fast, aggressive animal, propelled by rows of cilia all over its body. Here too, cilia waft particles into the gullet of a microscopic vorticella. Traveling in nanospace lets us better understand the forces driving tiny lives. Mites of the Acarus genus are not much bigger than those microscopic water creatures. They tend to live and breed under straw mats and carpets. Fortunately, wherever there are small mites, larger mites devour them. Nature always keeps her balance. That world, measured in tenths of a millimeter, will serve as our gateway, our introduction to nanospace.
Imagine what a barrier people crossed when they first looked through a microscope at the savage beauty of these tiny worlds. We asked, where did the quest for nanospace begin?
London, the Royal Society. Around 1620, Francis Bacon, who has been called the first scientific thinker, began discussing natural philosophy with like-minded friends. This was the start of the Royal Society. Its research tradition has been upheld by such scientists as Isaac Newton and Stephen Hawking. Among the Society's treasures, this copy of Micrographia, written in English, not scientific Latin, by Robert Hooke in 1665. His work with the microscope brought him lasting fame. Micrographia contains some of the most beautiful studies of microscopic observations ever made. Insects are precise to the finest detail. Drawings like these stimulated other scholars of Hooke's time. He even improved the microscope. This is a replica of Hooke's instrument. He created this device to focus light onto his specimens. It compensated for the poor quality of lenses, which could only magnify about 50 times. Not just his pen, but his mind was precise. In addition to studying insects, microscopic fossils led him to consider evolution centuries before Charles Darwin. Hooke is best known for showing that living things are made of cells. In fact, that word is his legacy to biology. The structure of cork reminded him of tiny rooms, the cells of cloistered monks. Hooke's word endures, his contribution with it. His discovery that living things are made of cells remains one of the key developments in all biology.
From a world of large cells to one in which life's beauty hides from us, disguised by tiny size. A great smooth wall of silica looms up, perforated by rows of curious symmetrical designs. It's the shell of a microscopic plant found by the billions in seas and fresh water, a diatom. Diatoms have distinctive shapes. This species is Cimbella. We saw minnow-sized fish eating water fleas. What do water fleas eat? Diatoms, like Gomphonemon. Look at this. Nature's perfection sculpted in silica, just thousandths of a millimeter long. Seeing nature's wisdom at this level, we begin to understand why computer chips are made of silica too. But that's another story. This realm is one in which strange dome-shaped objects rise and fall like tides beneath a giant moon. Perhaps they're living things growing and wasting on a flat, barren landscape of fantastical design. And let's not get carried away. When human breath fogs up cold glass with water droplets, that's what we're looking at right now in nanospace. At this level, substances change back and forth between liquid and gas. If you breathe on cold glass, it fogs. Step back, and the water evaporates. Breathe on the glass again, and so on. Like a jewel, nanospace has many facets. Many of its worlds we'll never see. Let's take a journey of a different sort in time to find out who unlocked the doors of nanospace.
1936 was the year of the Berlin Olympics. Television was in its experimental infancy. Using a beam of electrons to generate pictures gave electrical engineer Ernst Ruska an idea. Why not harness electrons to study invisible worlds? Ruska and his colleagues reasoned that replacing light with a beam of electrons would improve the power of microscopes. The project took 10 years. They produced the first useful electron microscope in 1939. What happens inside goes something like this. Just as light is focused by a lens of glass, an electron beam passing through a specimen is bent by electromagnetic lenses. A magnified image results. Resolving power was better than the best of optical instruments. These bacteria, Escherichia coli, are seen with an electron microscope. The same sample on the right was photographed with an optical microscope. Ruska had smaller targets in mind, viruses. These mysterious disease agents were invisible to light microscopes. It would be 1940 before Ruska finally photographed a virus. Just as E. coli bacteria live by the millions in the human gut, these tadpole-like T2 phages are viruses infecting E. coli. The electron microscope proved beyond all doubt that agents of disease were hard at work, even in invisible worlds.
Worlds within worlds within worlds. Electron microscopes plunge us into nanospace. How far can we go? However small the world we're looking at, there's always something smaller still. We ask, we seek, we discover, and we seek smaller treasures all over again.
The variety of available electron microscopes gets larger year by year. This one can study changes in the specimen being observed. This sequence records the growth of naphthalene crystals, a chemical used in insecticides. Just as ice evaporates on a sunny day, so can naphthalene. Here, potassium chloride crystals grow. Crystals of different substances grow in very specific shapes. This is because the atoms forming them are laid down in highly specific lattice-like structures. The great bricklayer of the universe never mixes up architectural plans. Each layer in this potassium chloride crystal is about 1/1000th of a millimeter wide, an orderly sequence of atom on atom, the structure of the crystal predetermined by the nature of its chemistry. The atom itself is the smallest coherent material particle, the ultimate goal of our quest into nanospace.
Hello again from Nanogate. Now that we've paved the way, we can journey to that ultimate of worlds, the realm of atoms. The atom is the brick, the building block, the basic unit of all elements combining to create the material aspect of our universe. This is the periodic table of the elements. In other words, a list of each type. In 1869, the Russian chemist Dmitry Mendeleev listed the elements from the simplest and lightest, hydrogen, to the heaviest and most complex. In a true stroke of genius, he left gaps in his periodic table for elements still to be discovered. Some we know well, others not at all. Among the most familiar, oxygen, hydrogen, carbon, and the chemical symbol for gold, Au. Hydrogen, helium, lithium, beryllium, nitrogen, iron, neon. The entire material structure of the universe is made up of about 100 different elements. They, in turn, are built of atoms.
Hydrogen, hydrogen, oxygen. Two hydrogens and one oxygen come together to form a molecule. The molecule for water. Carbon, 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 carbon. Carbon may form soot or coal or diamond. Let's try looking at the larger picture. Atoms are building blocks. Galaxies comprise the fundamental structures of the universe. Every star in every galaxy is made up of just 100 or so different elements, and elements in their turn are made up of atoms. Yet until very recently, nobody had seen an atom.
Gold, one of the heavy elements. Turning a bar into gold leaf gives us a better idea of the properties of the smallest material things. Atoms, making up each molecule of gold. A bar starts off about as thick as a wristwatch, 7 millimeters. Each time it goes through the rolling mill, it gets thinner and longer. Before this process is finished, the bar is a ribbon 15 meters long. By this time, the gold, rolled gold sheets, can be cut with scissors. At this stage, it would take 20 sheets to make a stack of gold 1 millimeter high. Next, sheets are put between pieces of paper, and the bundles sandwiched between soft leather. At this point, the gold is beaten even thinner. Even now, the process has only just begun. The sheets are cut up, bundled again, and beaten some more. To put this in perspective, a piece of gold that started as not much bigger than a man's thumbnail is now 2 meters long by 1 meter wide, the size of a single bed. In practical terms, the area of leaf that a gold beater makes depends entirely on his skill. At this point, the gold is 150 billionths of a meter thick, so thin that we can see through solid metal. We are looking right through nanospace. Even the finest craftsman cannot reduce gold leaf to fewer than about 750 layers of atoms. That is the first reason why electron microscopes have trouble spotting one among the many. It's like looking for a needle in a haystack.
Atoms, the principal entity in nanospace, as in the universe, don't easily reveal themselves. In this computer simulation, table salt is starting to dissolve in water. The orange and green balls show sodium and chlorine bondings in the salt. The small red and white ones are water molecules. We're slowing the reaction speed by a factor of perhaps a million times. Even so, atoms are in constant motion. That is the second major reason why atoms are so difficult to find. The third reason is that atoms don't have a solid surface. We refer to them as matter, but an atom is not a physical thing like a nut. Its nucleus is surrounded by a fuzzy cloud of electrons. Finding an atomic surface amounts to surveying the edge of a fog. In other words, seeing an atom involves detecting some thing on the edge of existence, moving at enormous speed and having no physical shape.
Rising to the challenge, Hatsujiro Hashimoto spent a long career studying atomic structures. A professor at the Okayama University of Science, Hashimoto is now in his 70s. 20 years ago, he was racing to be first to see an atom. Electron microscopes had reached a point where that goal was just possible. First past the post, though, physicist Albert Crew and his team at the University of Chicago. Next, the University of Toronto's Peter Ottensmeyer. Hashimoto and his team at the Kyoto Institute of Technology came third.
これは大変なものなんだけども、しかしこれはいつかは取れるというか、それで取りたい。それから顕微鏡なんかやってる人は最終的にそこへみんな向かっていくんだから、顕微鏡ですから顕微なんですからね。
But how does one detect an atom when its surface is just a fuzzy electron cloud? What happens is this. An electron stream passing through an atom is deflected by the forces it encounters. The electron microscope measures this deflection to create an image of the atom. Hashimoto's team used the element thorium in their experiment. A heavy element, thorium easily deflects an electron beam. First, the researchers dissolved their sample in water. The next challenge was to support it in some way in a vacuum. Tiny copper grids, 3 millimeters across, provide the foundation for that support. The wires lie just far enough apart to let a human hair pass through. The holes in this grid, however, are still 500,000 times larger than a thorium atom. The holes must be smaller. Hashimoto's team solved that too. When chilled glass is exposed to room temperature, tiny water droplets form on its surface. Then liquefied plastic is poured on the water-fogged slide, forming a thin film. The water droplets measure just thousandths of a millimeter across. Where the plastic film covers them, it develops cavities. The result is a plastic sieve with a huge number of tiny holes. When the plastic-coated slide is put in the water, the plastic sieve floats off the glass. The next stage is to mount the sieves on the tiny copper grids. The work is time-consuming. It demands a watchmaker's hands, combined with extraordinary patience and care. But even these holes are not small enough to retain atoms. So an atom catcher has to scatter tiny pieces of carbon dust across the plastic film. At last, the experiment is ready. A drop of thorium solution is added and left until it evaporates. When it dries, it will be ready to view. We hope to see thorium atoms at points where the jagged pieces of carbon dust restrict the holes in the plastic sieve. Detecting atoms visually demands slow, arduous routines. It is delicate work. This is how Professor Hashimoto did it 20 years ago. Others, of course, devised their own methods in the race to be first to see an atom. The black lines are the copper wires. The oval forms are holes in the plastic sieve, and the jagged shapes superimposed on them, carbon particles. The electron microscope focuses on a point where a carbon fragment partially blocks a hole. Hashimoto's team made almost 1,000 attempts to photograph an atom over a 6-month period. They failed every time. At last, a single photograph, 1 in 1,000, bore fruit. The large, bright areas are overlapping clusters of atoms. But Hashimoto's group was chasing a single atom. February 1971. At last, the team managed to capture a single bright blob, the mark of one atom. 380 years after the microscope was invented, researchers detected the presence of the elusive, long-sought atom.
The National Institute for Researches on Inorganic Materials in Japan houses the world's most powerful microscope. Just 20 years after a film plate gave us the first foggy image of a thorium atom, atom spotting is almost routine. In this pattern, that looks like blue tweed, every bright spot represents a single atom, a screen full of atoms. This image shows a sample of ceramic material. Now watch what happens when I clap. The atoms vibrate in response, all in unison. The sample is encased in a heavy steel microscope, but still it responds. Perhaps each human footstep shifts as many atoms in the earth as there are stars. Never forget, we are in constant touch with nanospace.
Nanogate can't travel into the atomic world as fast as an electron microscope, but we get there. We're at the atomic level, among the smallest material units of being. Around me, gold atoms, always in motion, always restless, as you can see. But even though atoms are always moving, as long as the gold is a solid, the atoms pack together in an orderly, crystalline, three-dimensional pattern. Of course, each element and compound has its own particular organization. Here we have two clusters of atoms, several thousand in each, merging into a single particle of gold. Looking at gold atoms assembling into well-defined, orderly rows, becoming a crystalline lattice of gold. In nanospace, in nature, atoms are in constant motion, as restless as change itself. Here's another tweed-like pattern with atoms drawn up in the rigidly ordered formation that nature intended. In this case, the separate bright and dark patches represent calcium atoms in a human tooth. The jewel among jewels, diamonds. Diamonds result from intense heat and pressure deep within the earth. Under those conditions, carbon atoms are crushed into the lattice which gives diamond its famed brilliance and hardness. The Greek philosopher Leucippus taught that all things were made of tiny, identical particles. His pupil, Democritus, coined the name atom. It means indivisible, because atoms were thought to be the smallest unbreakable thing. 2,400 years later, we stand among them.
scientific discovery and reward come slowly. Ernst Ruska's work gave birth to the electron microscope in the 1930s. His Nobel Prize for Physics came almost 50 years later, in 1986. That year, he shared the physics prize with two other laureates, Gerd Binnig and Heinrich Rohrer. Binnig and Rohrer won the Nobel Prize for their work on the scanning tunneling microscope, the successor to the electron microscope. A scanning tunneling microscope can reveal atomic structure in surface features using a needle-like metal probe. The tip of its needle lets the observer distinguish single atoms. A scanning tunneling microscope works like this. The needle is lowered till the tip is 1 nanometer, 1/1000th of a meter from the surface of the specimen. Electricity flows across this gap between the needle and the atoms. To keep the current constant, the gap must be constant too, meaning that the needle rises and falls as it travels across an irregular surface. Light microscopes use optical lenses. Lenses of electron microscopes are electromagnets. Scanning tunneling microscopes work differently. Just as a gramophone needle turns irregularities into vibrations called music, a microscope needle creates pictures of surface atoms. This extraordinary tool was created specifically to study the characteristics of atoms. In this case, the microscope's sample is silicon. The resolving power is such that we can see each atom on the sample surface. For a long time, researchers have wanted to study atoms of silicon, the element whose properties form the very basis of semiconductor chips. The scanning tunneling microscope has at last made this possible. Researchers soon discovered that their wonderful tool was even more versatile. The microscope can move single atoms. Soon, scientists were drawing by moving them around. Researcher Donald Eigler decided to announce the microscope's artistic ability in a very personal way. Using just 35 atoms of the element xenon, Eigler spelled the name of his employer, IBM. The result resembles sandcastles drawn in atoms, not sand. The world's smallest letters were less than 5/1000th of a meter high. That was April 1990. By October, the Japanese NTT followed suit. Then JEOL in November, and JRDC in time for Christmas. But the Japanese letters were large by comparison. IBM retained its record for the smallest and the first. Before long, Hitachi fought back for the Japanese. In the fall of 1990, electrical engineer Shigeyuki Hosoki launched his attempt on IBM's record. For his try at writing atomic letters, Hosoki developed a method of his own. When the needle of a scanning, tunneling microscope is closer than normal to a sample, the electrical current firing across the gap drives atoms out of the specimen. The result resembles blasting high-pressure air at a dusty floor. Hosoki intended to use this property to remove atoms one by one, thus forming letters. He He chose the very early morning of a November day for his experiment. There was no one around to clap, talk, walk heavily across the floor, or otherwise disturb the tiny denizens of nanospace. In less than 30 minutes, he finished his task. His letters read, Peace, 91. Shigeyuki Hosoki had successfully carved out the smallest letters in the world. Each one of these yellow peaks represents an individual atom of sulfur. Hosoki's letters were 2 nanometers high, beating IBM's record by 60%. 500,000 such letters in a row would form a line 1 millimeter long. This technology offers extraordinary possibilities. Some that come to mind are downsizing computers, increasing their memory capacity, creating new materials, investigating existing ones at atomic level to improve their strength or corrosion resistance. Nanospace has brought us to the threshold of a new technology, nanotechnology. For the past 50 years, the development of nuclear power has allowed us to harness the atom. Now we can see single atoms, move them, even build with them. Who knows what a future in the tiny, enormous worlds of nanospace will bring.
Descubra el espectáculo.